In this video, we're going to cover average atomic mass, and you should have read a little bit about it from the readings already. So hopefully this isn't super new to you. From the reading, you should know the average atomic mass, or atomic mass for short, of an element is a weighted average of the masses of its isotopes. And this is super important right here. It says weighted average, which is different than a normal average. And it's the weighted average of the mass of its isotopes. Now remember that isotopes, there are different versions of an atom of a certain element, and an isotope means that it's an atom of that element, but it's slightly different in its mass. Okay, it's because of the neutrons. Now, a weighted average mass reflects the masses and the relative abundances of the isotopes as they occur in nature. Okay, now there's this graphic from the text that's actually very, very helpful. So I'm going to try to explain this graphic. It says comparing abundances of bromine, chlorine, and silicon isotopes. So there's three different elements. We're going to look at each one of them, starting with the very left, where we have a blue pie graph. This is for the element bromine. And in nature, there's actually two versions of bromine. There's, right here, bromine 81, which has a mass number of 81. And then there is bromine 79. So this one is a little bit less massive. This has a mass number of 79. And by the way, in that reading, it also describes that these numbers can also be known as the atomic mass unit. Okay, so bromine 81 has an atomic mass unit of 81, and bromine 79 has an atomic mass unit of 79. Again, it describes the masses of each of these atoms. But since these are both bromine atoms, these are both isotopes of bromine, right? So the thing is, in nature, if you look at this pie graph, it looks like there's like almost the same amount, like 50-50 of each, right? But you'll see that bromine 81, there's like a little bit less. It's about 49%. That's just me estimating it here with my own eyes. And for bromine 79, it looks like there's a little bit more. It looks like there's like 51% of it. Okay, so I'm estimating these numbers based on the pie graph right here. And if you take a look at the atomic mass here, again, atomic mass accounts for a weighted average, meaning it's accounting for how many of each isotope there is. 49% of bromine 81 and 51% of bromine 79. If you take a look at the atomic mass, it says 79.9. 79.9. That's an interesting number. So I'm going to take a look right here and try to describe it like pretty much with a number line, okay? So on the left to the right, we have, I'm going to start with 79 AMU, okay, atomic mass units. And then on the right, we're going to have 81 atomic mass units. And in the middle, it should be, like right smack in the middle, it should be 80 atomic mass units, right? Well, the atomic mass of bromine, if you account for the relative amounts of each one of them, 49 and 81%, the atomic mass of bromine is a little bit less than 80. So 79.9 atomic mass units is the weighted average, right? So this is accounting for the fact that there's actually a little bit more, just a slightly small amount more bromine 79 than there is bromine 81. But because there is slightly more bromine 79 isotope, that means that, you know, the average is shifted a little bit more towards bromine 79. The mass is shifted a little bit more towards 79. It's not exactly 80 because 80 would imply there's 50% of each isotope, okay? Alright, let's take a look at one more example so that this makes a little bit more sense, okay? So now we're going to look at the middle example, okay? The middle example, we have chlorine. And for chlorine, there is also two isotopes. There's chlorine 37, and then there's chlorine 35, okay? And if you take a look at this, clearly there is a lot more chlorine 35s than there is chlorine 37. If I had to estimate it, there's about like 3/4 chlorine 35, right? So that's about 75% chlorine 35 compared to chlorine 37. For chlorine 37, it looks like there's about 25%, huh? Okay, so this one is like way further than 50-50. Okay, there's a lot more chlorine 35s than there is chlorine 37. And now let's take a look at the atomic mass, okay, the weighted average of all the chlorine atoms that there are. The atomic mass is 35.453, okay? Now let's think about this on a number line. So here we go, number line again. 35 atomic mass units on the left, and then there's 37 atomic mass units on the right. And in the middle we have 36, right? 36 atomic mass units. Now the actual weighted average is again 35.45. Where is that on this number line? That's going to be right about here, right? 35.453 is the weighted average. Okay, and again, this accounts for how many of each isotope there is. There is a lot more chlorine 35 atoms than there is chlorine 37. So since there's a lot more chlorine 35 atoms, the weighted average is going to shift more towards the 35 atomic mass units, right? That's why the weighted average is 35.45. Now let's consider, okay, well, that's what a weighted average is. And what's a normal average? Remember, a normal average, you don't account for how many there is. So for a normal average, there is chlorine 35, right? And then there is chlorine 37, so you add them. And then you divide by how many of them you added. There'd be 2, right? There's 2 isotopes. And this would give us something that's right in between 35 and 37, which would be 36. Okay? But this 36 amount is a normal average. And when we're doing actual calculations that involve the masses of atoms later on in our next unit, you have to account for, okay, in nature, there's actually more chlorine 35 atoms. So shouldn't we account for the fact that in nature there's more chlorine 35 atoms? Yeah, we should. We should. So we don't use a normal average then. It wouldn't be useful in this case to use a normal average. It'd make more sense to use a weighted average that accounts for how many of that isotope there is in nature. Okay? Alright, let's look at the very last example so that we can really understand this idea. In our last example, we have another element. We have silicon. Now silicon actually has, there's actually 3 types of silicon atoms, 3 different isotopes of it. There's silicon 28, okay, which has an atomic mass unit of 28. There's silicon 29, and then there's silicon 30, right? And if you look at the pie graph, well, at least to me, it seems like there is like roughly 85% of the pie graph belongs to silicon 28. So there's a lot more silicon 28s. For silicon 29, it looks like, if I had to guess, maybe 10%, right? And then silicon 30, maybe that's like 5%. And altogether, there would be 100%, okay, silicons. But there's more silicon 28 isotope than there is the other 2 isotopes. That's what I'm getting at. So this should be reflected in this weighted average in the atomic mass. So look at the atomic mass of silicon. It's 28.086. This should make sense because there's a lot more silicon 28 atoms. If there's a lot more, and this is factored in its average calculation, then the atomic mass should be closer to silicon 28. And it is right here, it's 28.06. on a number line, we have 28 atomic mass units, we have 30 atomic mass units, and in the middle we have 29 atomic mass units. But since there is so many more, literally 85% of it is silicon-28, then that average weight, accounting for the percent abundance, is a lot closer towards 28. Okay. Again, this is a weighted average. We're accounting for the abundance of the silicon-28 compared to silicon-29 and silicon-30. Alright, this is way different than a normal average. A normal average here would be 28, 29, and 30, right? A normal average is if you go, okay, 28 AMU plus 29 AMU plus 30 AMU, and since I'm adding 3 different isotopes here, I divide by 3. This would give me 29 AMU. Okay, that's a normal average, but it's not useful to have a normal average when we know that there is more silicon-28 atoms in our world. Alright? Okay, so what are we going to do with this information? Well, it's useful to know it for calculations later on, but you should now know it, how it's derived. And this information is so important that's actually included in the periodic table. Now, on the periodic table, we should already know a few things. We should know atomic number, right? The periodic table is organized by atomic number. And by the way, again, just as a refresher, atomic number is the same thing as the number of protons. Alright, that has to be in your head. Then there's the element symbol, right? And the element name. So the periodic table tells you the identity of the element. What element is this? Well, it's carbon, or it's nitrogen, or it's oxygen. And the very last number that we haven't looked at yet until now is going to be atomic mass. Alright, and again, atomic mass is also known as average atomic mass, and this is a weighted average of the mass of all of the isotopes of that element, right? And you're going to notice, if you look at the periodic table, a lot of the atomic masses are decimal numbers. It's because we're getting a weighted average, and that would get into the territory of, okay, it's going to be in between two whole numbers, so it's going to be a decimal number, right? And there's going to be some numbers, some atomic masses in the periodic table where it's actually not a decimal number. They're actually whole numbers. And you might be wondering, well, why do these have whole numbers, right? Why do these have whole numbers while the rest of them have decimal numbers? And this is actually due to something very simple. Some of these elements, there's only one isotope. Right? Meaning, like, for example, polonium. Polonium's right here. Polonium has a mass number of 209. So each polonium atom has an atomic mass unit of 209. Well, 100% of the time when we find polonium that exists in nature, all of those atoms are polonium 209. And if you're trying to get the average of something where there's only like one type, one isotope of, you're gonna get the same number, right? You're gonna get the same number. There's no in between. Every polonium atom has a mass of 209. So there is no decimal number. It's guaranteed, right? So that's why some of these are actually whole numbers. Alright, take a look at the bottom here. So from the periodic table, it lets you know a few things. We should know, again, atomic number. We should know the element identity, but now you should also know the average atomic mass, or atomic mass for short, okay? Now what are we going to do with this information? We're going to need to know how to calculate some things. And Here I'm going to show two examples, and after these two examples, you should be able to do the practice and get these pretty well. So please pay close attention to these two examples. I'm going to start off with the first one. Number 1, show the calculation for the atomic mass of carbon. Carbon has two isotopes. Carbon-12 has a percent abundance of 98.93%. Carbon-13 has a percent abundance of about 1%. So there's a lot more carbon-12s than there is carbon-13. And that already gives me information that, okay, if you're getting a weighted average, the weighted average is probably going to be closer to 12 than it is to 13, right? So anyways, let's calculate the atomic mass. It accounts for both isotopes, and this is actually very similar to the analogy of that bean, the bean lab that we did, right? So there's two isotopes, so we're going to be adding two things together. The first one, I'm going to talk about carbon-12. Carbon-12 has an atomic mass unit of 12. Now I'm going to have to multiply this by the relative abundance of carbon-12. Now carbon-12 has a percent abundance of 98.93. I need to turn that into a relative abundance, and just like from the bean lab, to turn it into relative abundance, I want to take this number and put it in its decimal form, which means I divide it by 100. Okay, so I'm going to just put that number right here. So that would be 0.9893. I hope you see that. It's not exactly the percent abundance, it's the relative abundance. And the relative abundance you just take by taking the percent abundance and divide it by 100. In other words, you can just move the decimal place 2 times to the left, like this. 1, 2, okay? 0.9893. Okay, what we're going to do now is we're going to take this, and we're going to add it to the other isotope, which is carbon-13. Okay, so plus, and carbon-13 has a atomic mass number, or atomic mass unit of 13 AMU, atomic mass units, okay? And then we're going to need to, again, multiply by the relative abundance. The relative abundance, again, is the percent abundance divided by 100. In other words, I take the decimal, the percent number right here, I take that number, and I move the decimal back twice. 1, 2. Okay, so if I take that number and I divide it by 100, it would be the same thing as this. Okay, this is the decimal form of that percentage. Okay, and that's it. Okay, since there's only two isotopes here, now I do this in a calculator. 12 times 0.9893 plus 13 times 0.0107. Okay, and then hit the equal button. So on a calculator, let's see, what is that going to give me? Okay, so this is what I'm getting, typing it straight in, and for this, it's just basic multiplication and addition, so it doesn't matter which calculator you use, you should still get this number right here. I'm getting 12.0107 AMU. Okay, that's the average atomic mass. Alright, and actually there's a way that I can check this. If I just look at a periodic table, I would be able to see and check whether this is the correct average atomic mass. Because again, the periodic table, in addition to it providing atomic number and the element identity, it tells you the atomic mass. So does it say 12.01 for the atomic mass of carbon? Let me check. So here we go. Where's carbon? It's right here. And yes, look, it's 12.011. This is pretty much the same thing, right? So this is checked. I checked it in the periodic table. You might be wondering, well, if it's on the periodic table, why do we have to calculate it? It's because I want you to know the idea. Where do these numbers come from? Well, it comes from the fact that there are multiple versions of that atom. There are multiple isotopes of that atom. and it's accounting for the relative abundance of them for you to get the weighted atomic mass, right? The average atomic mass. So it's the idea that I want you to get. I don't want you to just use numbers from the periodic table later without knowing where it came from, basically. That kind of makes no sense, using things and not knowing what those numbers are, right? Okay, let's take a look at the second question. Second question. We have copper has two isotopes, copper 63 and copper 65. Which copper isotope has a higher percent abundance on Earth? Okay, I'm not going to read the hint right now. So all we know is right now there are two isotopes of copper. There are two isotopes of copper. Okay. Now one of them is copper 63 and the other is copper 65. Now it's asking, okay, out of these two, which one is there more of, basically, on Earth? Which one is there more of? It doesn't seem like there's enough information to solve this problem. But remember, you always have a particular resource, at least in chemistry, that you should always refer to. Well, not always, but you have it to refer to, okay? And that's what the hint is. Hint, there's a certain table that will help, right? It's the periodic table. So remember, the periodic table tells you information about the average atomic mass. So let's find copper. I know it's right here. Copper it has an average atomic mass of 63.546, okay? So, atomic mass of copper is 63.456 AMU. Okay, and again, this is the atomic mass of copper, meaning it's a weighted average. It accounts for the percent abundance of all the copper atoms in the world. And if it's 63.456, you can imagine, okay, in a pie graph, which one has a bigger cut? Is it going to be copper 63 or copper 65 if we know that the weighted average is 63.45? Well, since the weighted average is closer to 63, that must mean that in a pie graph, right, in a pie graph, there must be a lot more copper 63 atoms than there is copper 65 atoms. Okay, there's more copper 63 atoms. That's why it's closer to, and when I'm referring to it, I'm saying the average atomic mass. That's why it's closer to 63. There must be a lot more copper 63 atoms. Alright, so the answer to this problem is it must be copper 63. And again, we had to look at a periodic table. We have to remember that the periodic table tells you information about atomic mass. And atomic mass, it has that a little bit of an idea of the percent abundance that's embedded into that number. Okay. All right. You should be able to do the next problems 1, 2, and 3 right here. Okay. So I'm gonna ask you to pause the video, try these problems, and then unpause the video to see if you got it correct. All right. So pause the video right now, try it. In just a second, unpause the video, see if you got it right. Alright, so there are the answers right there. You can take a look and see if you got something similar.